From my side, I hope you are enjoying this school. And today I'll talk to you about Alice. Alice is not a tiny, beautiful girl. It's Alice. It's this one. Is a spectrometer. The weight is around 10,000 tons. And you see the size of this experiment comparing to two people here. So it's really a huge experiment, one of the 4 experiments at LHC, but we will talk about this in a moment. So what's the main purpose? So we have to understand the very first moments of our universe just after the Big Bang. This meaning that we want to really go back in time for something around 14 billions years. By the way, just stop me if you don't understand, if you want that I repeat something. So it's a dynamic seminar, this one. Yeah? Just stop me and then I can go back or explain again. So we have to go back for something like 14 billion years. Why? We are more or less, so if you see really the history of the universe from the Big Bang and going up to today, we want to focalize in this region. This region, it's called Quark Gluon Plasma, the matter of the universe. We are around 10 to minus 6 seconds from the Big Bang, so 0.0006 times seconds, and where the temperature was around 10 to the 13th degrees. And then the migration, if you want, the change of the universe between the quark gluon plasma and the protons and neutrons, so the standard matter. Well, let's. What does it mean to go back in time? So the evolution of the universe is the following. Again, Big Bang, we are here, around 14, 15 billion years. We know that the temperature of the universe is around 3 Kelvin. Yeah? This is the background radiation of the universe. If you want to study what is going on now in the universe, you are in the field of the astrophysics. So galaxies, stars, planets, and so on. If you want to stay in the biology region, where you can see the formation of the so-called organic chemistry, or the cells, and all the animated individuals, you have to go back something like 1 billion years after the Big Bang, when the temperature was around 18 Kelvin. If you want to understand in the chemistry region the formation of the atoms, you have to go back around 300,000 years from the Big Bang, where the temperature of the universe was 6,000 degrees. So if you want to stay in the nuclear physics or subnuclear physics, you are in this region where all the particles were produced. All the forces, in some way, were came out from the Big Bang. And we are in the region between 10 to the minus 34 until, let's say, 1 minute, more or less, from the Big Bang. And the temperature is the following. So around 10 to the 27 until 10 to the 9, so 1 billion degree. If you want to really stay in the frontier of the Big Bang, you have to stay in the cosmology environment, and this is not what we are going to talk today. So we are in the region of subnuclear and nuclear physics. So going back in the universe, in the time, means that we want to have the same energetic conditions, so the same temperature that it was at that time, to have, again, these particles that were produced at that time. So we have to understand the deepest nature of the matter, so we have to, as I just said, create the initial condition of the universe. Because we want to create who is carrying the information. So we have to create the particles that are have been created at that time. Of course, these particles don't exist anymore now because they have a lifetime. They decay after really a tiny fraction of seconds, and they disappear. They go in other particles. So after so long time, we have only the stable particles now, like protons, neutrons, electrons. We will see these things. But all these particles that were produced at the beginning of the universe decayed, so we want to again these particles to extract the information that they are carrying. And in which way we do this? We do by the particle factories, so the accelerators. I guess, I don't know if you have already had some lessons about this. Anyway, accelerators are working mainly by this formula that I guess you well know. There are all the T-shirt, cups, teacups, and so on. So basically it says that there is a relation between the energy and the mass. So what we do? We take mass. For instance, in this LHC that I'm going to show you, we take two protons, a proton and a proton, and we collide these particles at very high energy. So we are on this side of the formula, mass, very high energy. They collide, and they go to this side of the formula. We have energy. From this energy, we go back to the right-hand side of the formula, and we produce again mass. But now we don't have the mass of the beginning, so the protons. We have the new masses, so the new particles, what we want to produce. Is it clear, this process? So this is, let's say, in a very naive way, the way that in which the particle factories, so the accelerators, work. And I don't know, maybe you have seen already this guy, Ada. It's at the entrance, or more or less, of the lab. So you know the story of Ada. This was the first collider ever built here in Frascati by this guy, Bruno Touschek, in the '59. Then we had Adone. Ada means anello di accumulazione. Adone is a large Ada, or if you want, a beautiful machine that worked from '69 until the '90s. Then there is Daphne, that I guess you visited already. And then this is the largest, biggest, most energetic accelerator ever built. Is the LHC, Large Hadron Collider, that is running at Geneva, at CERN, from the 2009. So this is the track of the accelerator, is 27 kilometers long, 100 meters below the ground. Here, just for comparison, you see this is the airport of Geneva. This is all the CERN campus. And you can imagine how energetic they are, these particles, because they do 11,000 turns per second. So each second, these particles do 11,000 turns long, 27 kilometers. So you can imagine the energy that they have when they collide each other. So, of course, this adventure started something like 20 years ago, because you need really a long time to understand what you want to do. And this is another interesting stuff that maybe we can discuss at the end if there is some time, because you have to tune your experience, you tune your work to arrive after 20 years to have something that is well advanced, but not too much that you don't have tools, or is not too old that maybe you are using computers that are already 5 years, 10 years old. But anyway, this we will discuss. So this global adventure started 20 years ago. This is, you see, the excavation of the holes, of the caverns. And then this is a picture of the accelerator. So you can imagine this tunnel long 27 kilometers. Here, these are the magnets that are bending, compacting the particles, and inside these are two holes where the particles are traveling. This is the accelerator control room. full of people. All these islands here you see, it's a little kind of flower, are for the different accelerators, because you don't have only the largest. From here you can see. Exactly. You see, there is another accelerator here, there is this accelerator here, and other few things here. Because you don't inject you don't use just the largest one, but you have to arrive step by step to the largest accelerator. So the particles must be prepared in the small accelerators, and then you go to the final one. This takes a couple hours. And you can see these areas are really to manage to work on all these different sub-accelerators. Good. And this is the participation. So you can see the full map of the world. So except the white countries that you can understand mainly for economic reasons, all the others are participating into CERN, into the ALICE-LHC. The blue countries are the owner, let's say, the member state of the CERN. All the others are participating, paying the participation. But so Italy is one of the main country at CERN, and you can see there are something like 6,000 plus 3,000, so more or less 10,000 countries are working on this project. Maybe you can find your country here in the list. Good. So there are these. You can see another picture here. This is the accelerator, more or less 100 meters below Earth, and the 4 spectrometers, the 4 experiments that are mounted. There is LHCb, ATLAS, CMS, and ALICE is the one that we are going to talk today. So 4 gigantic caverns host huge detectors that I will show you. The center of mass energy, 14 TeV, this is the energy, the unit that we use, never reached before, something very enormous. The beam intensity is also order of magnitudes higher than before. And all the accelerators is something like 40,000 tons that are cooled down to the helium liquid temperature. So everything is superconducting. So the temperature of the full magnets is around 2 Kelvin, 2 degrees. Well, this is, for instance, the largest, the biggest experiment, ATLAS. You see the size of people here. So you can imagine you take the lift, you go down 100 meters, and then the doors open, and you find a kind of huge building just in the ground. Good. This is another picture of ATLAS. This is during the mounting. You see a guy here. This is the front vision. Here, the beam is coming from one direction and from the other. And this is ALICE. Then we will, of course, come back to ALICE, but just to show you the picture, this was during the mounting. This is the magnet of ALICE, a guy here. You see the tunnel here where the LHC, the accelerator is coming. Good, but now, after this brief introduction, we have to understand the bricks of the universe. And to understand this, we had to talk in a couple of slides, not more, about the standard model. The standard model is what we think is describing the universe. Starting from the 70s, physicists have been working on the standard model, and now we really believe that this model is describing the universe. There are a lot of problems, there are pieces missing, but the model is quite satisfactory in describing what we see in the accelerator, in the universe, in the tiny matter. And this is the basic table of the standard model. So this is something that you should print and put in your wallet, because everything is made by these pieces. We are made by these pieces, all the things that are around us, the universe, stars, and everything. So what do we have? We have this. I don't know if somebody already explained you this. Have you already So I don't go really in details. But anyway, these are the quarks that are the bricks that are forming the composite particles, like formed hadrons, protons, neutrons, kaons, and so on. These are the leptons that are more aristocratic. They stay alone. They don't mix to anybody. They are electron is going around the nucleus, you know, muon, tau, the corresponding neutrinos. And all these, the bosons, are the mediators of the forces. Then there is the Higgs boson that is a kind of director of this orchestra. I guess also in this case somebody explained you what is a Higgs boson. Good. Then we have forces. We have 4 fundamental forces. We have the gravitational, the weak forces, the electromagnetic, and the strong. So the weak, it's called weak, but if you think that the gravitational is 1, the weak forces is 10 to the 29th times the gravitational, and is responsible for the decay. I told you at the beginning that when we produce these particles, most of them decay, because there is the weak interaction. For instance, a neutron, just alone, after a bunch of seconds, decay in a proton, electron, and antineutrino. And the mediators are the W and Z boson. Then there is electromagnetic force, that is one of the most known force, keeps together the atoms, is responsible for the light, for our cell phone, and so on. So 10 to the 40. The mediator is the photon, and then the strong force. The strong force keeps together the nuclei. Is the strongest, and the strength is 10 to the 43 comparing to the gravitational, and the mediator is the gluon. So we have already a lot of pieces here. We have the quarks, we have the mediators, we have the gluon, and if you see these forces, you know there is a kind of study to think that to try to understand if the 4 different forces are coming from one unique force. And we are already in a good path, because these 2, weak and the electromagnetic, are already together. We now talk about electroweak force. For the strong, we are working on this. Gravitational, nobody knows how to do, but this is another story. So, and what we have to really understand in our experiment, in this beginning of the universe, in this early universe, mainly is the strong force. And now I will tell you why. So we will concentrate our force in the quarks environment and in the strong force, because this is the force that is acting among quarks, among gluons, so among the bricks of the matter. So, and then we have to, in some way, go back. You have to think that really this Big Bang theory is something that is working. You know, this is a theory, is the most believed theory, but nobody knows if it's the real truth. In any case, we define this our beginning of the universe. Well, so we want to do a mini bang in the lab. So we want to produce our Big Bang in the lab, or stay really, as I told you at the beginning, close to the Big Bang. So we need a small system that can be accelerated to ultra-relativistic speed. I told you that we want to produce this particle. I cannot take a tennis ball and then another is too large. I have to take something tiny that I can accelerate to very high energies. The high energies really is even larger than 19.9999% of the speed of the light. Is really the system that is close to the speed of the light. But this system must be large enough in order to have a chunk of matter, not just a single particle. For instance, when you heard about the Higgs discovery or also other accelerator here or Daphne, what you have single electrons that are interacting with other electrons. Or you have protons in case of Higgs with other protons. But this is too tiny, so you can produce the energy to have the Higgs boson. But you don't have a kind of a chunk of matter to simulate, to recreate the early universe conditions. Is it clear? So I need something that is tiny because it must be accelerator. But I need something that is not infinite, small, but has some dimension because I want to study the early universe, the evolution, the thermodynamic properties, and so on. So what I do, I use AD ions. So LHC, in this case, when we want to do these studies, meaning more or less 1 month per year, is accelerating ions of lead. They are tiny because they are around 10 to the minus 14 meters, but they have a finite volume that can be exposed to pressure and temperature. You cannot do this with electrons or protons. So we have to we will try to force matter through a kind of phase transition that I'm going to explain you. Then this new phase is called Quark Gluon Plasma. So you know what is a quark, you know what is a gluon, I already just tell you. And this matter of the universe is a plasma that we will see now. So you can, I don't know if you see this video, let's see if it's simulating two nuclei. You see here a nuclei of lead, and here nuclei of lead colliding. So they arrive, they interact, they create the new particles, and these particles are traveling, will travel in the detector. So we can reconstruct these particles. Look at this is are the dimensions. If you want also the time scale. So it's really, so dimension, we have something like here, few Fermi over C. So meaning these are nanoseconds. So everything happens in few nanoseconds. So there are the ion coming, the interaction, and then there is a quark gluon plasma forming, and then the particles are produced and traveling into the detector. But now I have a question to see if you are smart enough. I told you that we use lead ions that are, so it's a nucleus of a lead. And in my mind, they are kind of a sphere, they are a kind of ball. But here, somebody made this picture depicting this as a kind of disk. So is it a mistake, or you have an explanation for this? That is the same. So we have two answers that are both correct, because it's the same in any case. Yes, they are traveling close to the speed of the light, so they are contracting. The space is contracted in the direction of the motion, and then you see that it's really this direction is contracted more or less to really a tiny film, because the speed of the light is close to the speed of the ion is close to the speed of the light, and you see that they are interacting in these funny shapes. Then you have the particles produced, and then they are traveling into the detectors. Good. So now we are back to our ALICE. ALICE is not just a name; it's a nice name. I don't know if somebody of you is named ALICE, but means a Large Ion Collider Experiment. Because ALICE is the only detector among the four that has been built specifically for this kind of physics. So all the other detectors are multipurpose. Also, ALICE is multipurpose, but is devoted to this kind of physics. So to reconstruct, to study this heavy ion interaction. So, and here you see this is the beam line going through. So particles are coming in this direction. Other particles are coming in this other direction. They collide here in the center, the so-called interaction point, and then the particles that you saw before are traveling here into these detectors. They are all specialized detectors, and then we have to reconstruct. So we have to reconstruct something like 10,000 particles produced for each interaction, and each interaction is happening each 25 nanoseconds. So each 25 nanoseconds, we have 10,000 particles produced. This is a huge amount of data that must be elaborated. So this is another picture of the experiment. These doors are the doors of the magnet. This is the largest warm magnet, not superconducting magnet ever built. When everything is ready to start, the doors are closed in the way that the field, the magnetic field, it's a solenoidal field, is contained inside the spectrometer. And this is another picture. You see the size. This is a guy here, another guy. So this is a huge detector. This is the beam line of the LHC coming into the center of the spectrometer. So here there is another simulation that I can show you. Again, this is inside the ALICE spectrometer. You see, this is the ground. We are 80 meters here below the ground. So the beam line of LHC. This is the red magnet. You see the detectors inside. You see the bunches of particles that are traveling here, coming, and they interact in the center. Here, you see the nanoseconds are passing, and all these lines are the new particles produced and are traveling into the detector. So after a few nanoseconds, they will travel, they will be detected, and after 25 nanoseconds, we are ready to take the other bunch, the other collisions that are coming from the LHC. And this is continuous. So it's during the day, during the night, during the holidays. It's a continuous collecting data. So, and this is the Quark Gluon Plasma. So it's a kind of soup that we understood has been at the origin of the universe. So the early universe was a kind of a soup or quark that you know, gluon that you know, and is a state of matter called plasma. Why to study the QGP, which are the main feature of the QGP? And really it's possible to have such system in the laboratory, because I told you that we are talking about something like 2,000 billions of degree that we have to produce in the lab. And imagine that the temperature of the sun is only around 15 millions. So we have to produce, as I told you before, a mini Big Bang in the lab. This is the most difficult slide of this seminar. So you have to really pay attention here, because it's really fundamental concept. This is so-called asymptotic freedom or confinement. It is at the base, at really the ground of all these understanding of these physics arguments. So I don't know if you are already so expert to identify this as a particle. We have two up quarks and one down quarks. You know what is that? Proton. So you are really smart. Huh? So I'm quite scared about this, but okay. And they are, what does it mean? They are more or less free inside the proton. So if you consider the potential of the electric force, the Coulomb force, this you have studied at school, you see that they are proportional to the charge. They are they goes like 1 over r, 1 over the distance. So if you are taking the two charges at longer distance, you see that the potential, the force, goes down. So you feel less strength of your force. Yeah? This is clear. If you take two magnets, you feel a strong force where really close by, but if you take a bit away, you see that your force is decreasing. But if you are in the regime of the QCD, so the strong force, the quantum chromodynamics, one of the fundamental forces that I showed you before, the behavior is completely different. There is an exponential law here, and r stays here. So, oops, sorry. What happened here? Okay. So this means that when the particles are close to each other, like here for the protons, they basically don't feel any force. Yeah? You see here is more or less 0. They are free, asymptotic freedom. But if I try to take a quark and pull it away, the force increases a lot. So it's a kind of spring. If I try to, they are free, I take a quark, I try to pull it out, but it doesn't come. So there is a really force that is generated among these quarks. Okay? And so separating interacting quark creates a tension, so an energy between quarks that is able to create new particles. What does it mean? You see, I have a quark, an anti-quark. I try to separate. There is a tension here, but this tension at a certain point has an energy that is able to generate new particles. It's clear, this concept? Okay? So remember again this formula that I showed before, E equal mc squared. Yeah? Is the same. We have energy that we can produce mass. So here, in this interaction, I can produce new particles. So let's take the colliding particles. For instance, they produce two quarks, a charm and anti-charm. They separate each other, but here the tension is really strong. At a certain point, this tension has the energy to produce a D and anti-D, for instance. And this D and anti-D, they separate. This tension is not able to produce any force because now the energy is low. And these two quarks are coming together and produce two new particles, for instance, a D minus and D plus. So this is called hadronization. So as I told you, this is really an explanation for dummies, for beginners. But this stays really is the basic argument for the production of the particles. So we will never have an isolated quark. We will always have formed particles, so complex particles, because we cannot have a single quark alone because of the behavior of the QCD potential. Okay? And so what does it need? What does it mean? That to create the system at the beginning where all the quarks, all the gluons, this plasma was at the beginning of the early universe, we have a negligible strong interaction. So we have to put all these quarks and gluons together to have this potential close to 0. Otherwise, they don't stay all together. Yeah? They are able to form new particles. So we have to really compress these hadrons to form the Quark Gluon Plasma and to have a soup of these particles. These concepts that I roughly show you are the argument of the Nobel Prize in 2005, given to Gross, Polizek, and Wilczek. So, and then we can really study the phase of this matter. So if you consider normal matter, for instance, the water, you have the solid, the liquid, gas, so you can really draw a phase diagram with the ice, with the liquid, the gas, triple point, the temperature, pressure. This is something that is well known if you study thermodynamics. Then there is a fourth state of matter, is a plasma, so meaning all ionized particles. You have sparks, solar corona, a lot of systems that are in this plasma state. In our case, in the QCD, so in this early stage of the universe, we can really draw something similar. So it's amazing that we can have a phase diagram for the universe. So here we put the temperature, here we put the density of particles. The early universe stays here, so very high temperature, a very low density of particles. I told you it's a soup of quarks and gluons. LHC stays here, so really close to the early universe. Very high temperature, very low particle density. And all this part is the Quark Gluon Plasma, so the soup that was at the beginning of the universe. Then, if we cool down, you know that the universe in its expansion cools down, we produce hadron, so particles, nuclei, nucleon gas. So all this is the ordinary matter, and all this here is the Quark Gluon Plasma. Then there are also specific things. There are neutron stars that are in this region that are in some case are a source of Quark Gluon Plasma. We have color models, color things, super color products, but okay, we don't enter in these details. And also in this case, we have some critical point with all the phases are together. So there is a strong similarities between the normal matter and the QCD matter of the early universe. So where we can produce the QGP, of course in the Big Bang, but this already happened. We can simulate it. It was simulated for a long time on computers. It's called lattice, so a kind of technique to study the Quark Gluon Plasma, to study the QCD matter. We can study a neutron star or supernova from this, but I mean, this happens only once in a while. We don't want to spend too much time. And then we have LHC that is able to produce these things. And this is an event. It's a simulated event, but it's a well-simulated event. All these lines you saw before are particles produced for each interaction. Each time we produce the Quark Gluon Plasma, then we have the particles that are flowing through the space, and then we have to detect and study what is going on. So it's a problem. This is a problem because we have to really handle huge amount of data. We really don't have a single computer so powerful to study this data. If you think that we produce something like 1.3 gigabytes per second, so per second we produce 6 times the Britannic Encyclopedia each second. So it's really a problem to handle this data. If we put all the data on DVD, on CD, you can have a stack of 20 kilometers of CD per year. So we we have a solution for this data by using a grid. A grid is a kind of really grid. It's a kind of a connection among several computers, computing center over all the world, that each computer center can elaborate a tiny piece of this data, and after all the running of the codes, all the running, the processing of the data, they come together. So if in my office, I just submit a job of my analysis, a tiny piece goes to New York, a tiny piece goes to Tokyo, another goes to Geneva, another stays in Rome, and they are able only to analyze these tiny pieces. After that, they come together in my office, and then I have the final results. So this is the only way to handle this data. So this soup is really rich of information. Of course, I mean, I cannot enter in all these details. We have a space-time evolution of birth of hadron, all the QCD phases, plasma, color, Gaussian instability. So everything is able to identify, everything is able to define what happened at the beginning of the universe when the strong force was created, when the quark and gluons were created, ready to start, ready to form new particles. But I mean, they are too specific to discuss in this lesson. What I can, for instance, told you is that the early universe behaved as a perfect fluid. So this is something that was discovered only in the last year. So it was not a gas, it's not really a plasma as we can imagine in a classical way. It was a perfect fluid. So you can imagine 1 million of seconds from the Big Bang, we had a kind of perfect fluid. And then we can enter in more details. We understood what was the energy of the universe. We understood the volume when the freeze out, so when the particles are already real particles and not just a chunk of quark and gluons, the time scale, so everything happened in something like a few nanoseconds, so Fermi over C, 10 Fermi over C. There is some also hydrodynamic calculation that we can perform. So it's really a fluid that it's evolving. And then we also understood all the phases of this evolving liquid. And then, okay, other specific stuff. We can also, speaking about universe, produce black holes. So we are going back to the early universe. In principle, we can do something close to black holes. These black holes are not really black holes, as you can imagine from a movie star, but it's mini black holes. These are, in principle, potentially produced. Up to now, nobody has seen any black hole, mini black hole. But they are really tiny. They are extremely hot, and what is happening, they evaporate. So if we will ever produce any black hole, they are not sucking matter, but they evaporate, forming something like this. You see, this is simulated event by CMS. And they will produce this spheric event, producing 75% of quark gluons, some charged leptons, neutrinos, some photons. So we know in which way they will show us, they will come, but at the moment there is no evidence for this. Anyway, we are really far away from any cosmic black hole. You see, a cosmic black hole has the energy of 10 to the 19. This was the energy of the early universe. At LHC, we are at 10 to the 4th. So there are something like 15 orders of magnitude between the energy of the LHC and the early universe. Anyway, this is the machine, the study that is closer to the early universe than everybody else. So, conclusions. So in this way, we will have a few minutes for discussion. ALICE and LHC are operating wonderfully. Really, now after 2 years of a stop, because LHC stopped for 2 years for renewing, for reparation, for installing new pieces, new spectrometers, is starting again. Around May, we will start again for data taking, and this will continue until 2018. Then we will have another stop, another upgrade, and the LHC will continue until 2025. So you will have time, if you are interested, to work in this project. And then after 2025, we should understand what to do. Anyway, and there is a new and unique area for the exploration of the matter. This just started, And the connections with a lot of other branches of physics are incredibly high and intriguing. If you are interested, then you will download this presentation. There is a video here where it's me again that is showing the experiment. I'm going really into the experiment, explain something. Unfortunately, it's in Italian, but OK, you can at least see the movie and understand a bit more about ALICE. So thank you very much.